All right, welcome. This is a quick video tutorial on oversampling and filtering. So what I have here is I have a program, and we can take a quick look at the block diagram. Basically what this guy does is he'll create a sample waveform that I want to measure, and we'll create two types of noise, random noise and periodic noise. And then I have a routine to do an oversampling filter, some oversampling, and then I have a low-pass filter routine as well. So we'll look at those in a second. Basically the way this works, if I run him, well, I get a sine wave and I can change the frequency and the amplitude of my sine wave if I want. So there we go. So that would be the signal, and the world doesn't always present the signals to us the way that with actually just our data. Sometimes we get lots of other stuff along for the ride. So one way that might be is we might get random noise. And as it sounds, random noise is random. There's no real pattern to it, and in this guy I can change the amplitude of my random noise. I can completely swap my signal if I wanted to. So there's a pretty noisy signal, and the random noise here just comes from a random number generator, and we multiply in, or we just add that in. I also can have periodic noise. So here's an example of periodic noise. That's a lot. So there's some, and this is just 120 hertz sine wave floating on top of my signal. And this happens quite often also. 120 hertz being 2x 60 hertz, which is the frequency coming out of the wall. Most common one that I see. Definitely see some 60s, some 180s, some 240s, but 60 hertz noise and its intervals going up are the most common form of periodic noise that I see. And again, here we just took the frequency of the noise and added that waveform in. So there's just three waveforms: random, periodic noise, and then our base signal. So I can generate a waveform with a couple different types of noise. Turn that noise back off. If only it was so easy in the real world. And I'll turn the random noise back on so we can look at that a little bit more. So there's a signal that's pretty noisy. So I've got two types of filtering here. The first one is oversampling. And what oversampling does is it basically says, all right, gather the data at some factor faster than we actually need to display it, and then downsample. So in this case, I'm going to gather the data 100 times faster. And so if I turn on oversampling, well, sure enough, I pretty much get my original waveform back. So oversampling does a really great job at removing random noise. And it makes sense, right? So now I used to have one sample that had my signal and random noise in it. And now I have 100 samples, and if the noise is truly random, those 100 samples will average down to something that's pretty close to the actual original value of the signal it's trying to measure. So oversampling does a really great job at removing random noise. And here what I did is I just took the waveform, and of course with oversampling I had to generate 100 times more points than I did to start. And I took those guys and I just averaged them down, so every 100 points becomes a new waveform, or one new point. So the thing with oversampling is the more oversampling you do, the cleaner your signal is. In fact, the noise goes down like the square root of your sampling. So there's a factor of 10, there's a factor of 100, and there's a factor of 1,000. Looks an awful lot like our original waveform. So oversampling is great. The good news is that it's nice and inexpensive, because A to Ds are nice and cheap, and so oftentimes we can sample really, really fast, and we can get some good results with that. So that's oversampling. So I'm going to go back, turn the oversampling off, and turn the actually, then I'll talk about back to my periodic noise. So here is a fair amount of periodic noise. So I have another type of filter here called a low-pass filter. And a low-pass filter, it's a digital equivalent of an analog filter, where you basically say, all right, there's a cutoff frequency. Or in this case, I'm going to set the cutoff frequency at 40 hertz. Because in this case, I have to know some information, right? The frequency, the signal I'm worried about is this big 5 hertz wave. And the noise I'm trying to get rid of is this 120 hertz wave. So I have to say, all right, well, I've got a 40 hertz cutoff. And sure enough, the low-pass filter removes the periodic noise, which is great. And I have a filter order here. Essentially what happens is that frequencies below 40 hertz will be passed, and frequencies above 40 hertz will be attenuated. The order is 6 dB per octave. So this is going to be 18 dB per octave. So once you get, a factor of 2 above 40, so we get up to 80 hertz, we'll be down by 18 dB, which is actually quite a lot, coming up on 10x. So low-pass filters actually work very, very well for our periodic noise. And granted, we have to know something about the cutoff frequency. What's the penalty we pay here? Well, we have to do a bunch of extra math. And if the frequency we want to measure, say this is 38 hertz, and the noise is 50 hertz, the filter's not going to do nearly as good of a job. So I'll have to set, in fact, we could do 30 and 50. And you can see that aliasing now, that beat frequency going on. So I could turn the filter order up, and sure enough, we'll get more and more to the 30 hertz wave and less to the 50. But the penalty I pay here is in delay, because every order I add extra delay to the system. I'll turn my drive frequency back down to 5. I will turn my noise frequency back up to 120, and I will turn my filter order back down to, say, 2. 3, 4, there you go. That's a nice compromise. All right, so then, well, here's my periodic noise again. Oversampling doesn't do anything for it. You notice I turn the oversampling on and off, I get very, very small changes, because I'm just oversampling the actual periodic noise. So the oversampling filter doesn't do much for periodic noise. Turn my periodic noise off, turn my random noise back on. You can see it random bouncing around. Again, oversampling works very well. Low pass filter, what do you think is going to happen? Yeah, not a lot. We filter some of that out, but you can actually see the data is still just as jumpy. So again, low pass filter doesn't work very well on random noise because, well, it'll get the random noise that's above the cutoff frequency, but it won't get the random noise that's below it. So that's a brief tutorial on oversampling and filtering. And let's see. And there would be a waveform that you can definitely see the sine wave in here, but we've got both periodic noise and random noise on it. And sure enough, with some oversampling and some filtering, we can get a nice clean waveform back. Hope that helps.